Hello and welcome back to my channel plasmatweeter.de. My name is Ulrich and in this episode I will show you the building of the power supply for our Ionovac Replica. And I think we do some measuring about this Ionovac that you can see that is nowadays also a really good tweeter. Okay, let's start.
Okay guys, here is the circuitry of the DuKane plasma speaker, and today we talk about the power supply, which you see here on the bottom. So this is the power supply for the states. This is 170 volt main input, and you see here a voltage doubler. So the voltage is doubled from 117 to 230 volts. So at this point here we have 230 volts, and we have here diode, we have the first resistor, we have the two filter caps, the second resistor, and we have then here the modulation transformer, and this goes out to our circuitry. What we here see is the heater transformer. It's directly from the main, and the heater transformer goes with one point to the circuit ground, and with the other point to the heater of the tube. So what I like to do is I would like to make a PCB for the circuitry, but there's a little difference because in Europe we have 230 volt main power, so we don't need this voltage doubler. So what you here see is the circuitry we saw in the DuKane original circuit with the two resistors, with the filter caps, and directly the output. So here I have the input for the heater transformer. So one leg is also going to the circuitry ground, and one leg is then going to the oscillator. So if you look now the board, I made it already. This is our little circuit board. It's 100 millimeters to 80 millimeters. We have here input of the main power, input of the heater transformer. We have the diodes. We have in the middle here the filter caps, and on the right side we have the output. So this will be the little circuit board. And we can also look at the bottom. And the bottom you see the copper wiring of the circuit board. So now we can upload this to our PCB manufacturer, and we have a PCB manufacturer in Europe sitting in the Netherlands, and I sent him this, and on the website you can then directly see how the circuit board is made. So I show you this in a moment.
So today guys arrived the PCBs, and let's open the package. Looking what is in. Okay. Wrapped around. Hey, looks nice. Really nice. And Let me see if the part will fit. Yeah. That's really okay. So I have this made for different sizes of caps, so for the smaller ones and for the bigger ones. And also the other parts, fuse holder. Yeah, fine. Diodes. Looks nice. We can begin. Now we have to solder our board, and therefore I use this solder box. These are very rare, very seldom to catch. Maybe you found some on the flea market, but they are really very seldom because they are made out of cardboard. And I think that's the reason why they are not available nowadays. It's made by our old-timers. So it's relatively easy. So it's a box, you see, it's empty box. And we put in our PCB and we are putting in our parts. And not to forget, solder wire. Solder wire. I think this is enough. Solder wire. Yeah, and now very carefully. And what we have now to do is, this is the magic weller. With the magic weller you have to wipe over the solder box. Wipe over the solder box. And it takes not long because the PCB is not large. And we have here, wow! It's always a pleasure. These solder boxes are great. So now we have the finished PCB, huh? That's really good. So, and now we are mounting this in our case. So I have a little case here. That's the top. That's the bottom. I prepared it already. And this goes in here like so. And I have also prepared the back side with the heater transformer and main input switch. This goes in here like this. And for the front side I have prepared this panel with the modulation transformer and with potentiometer from Visatone. This is the input. This is an LPAT resistor. These LPAT resistors guarantee that there is always 8 ohm impedance on the input clamps because they are functioning like 2 potentiometers back to back. So this is for volume control, and this is the cable which goes then to our oscillator case, and this will be here in the front. So this will be our power supply. So now we make this. I think I make it off camera. It's a little bit boring to put all these things in and the wiring and so on, and when it's finished I'll be back. Now I have assembled our little power supply here. It's finished so far. You see this is our PCB. Schematics are according to the original DuKane. We have our modulator transformer, we have here the heater transformer, the main input, and here is the input from the frequency crossover. and this is the volume control. So, believe it or not, I have not switched on it so far. I'm trusting my expertise. So I have already wired this to our Ionovac Replica. I have here a cord from my Helvet Packard function synthesizer, model 33258, and I will connect this here to this input jacks. So then the power cord, and this is now running over a main separation transformer here in my back. I will not power it on directly from the main. I'm using a main separation transformer. Maybe something is smoking, I don't know. We will see. So, switching our power on, switching this power on. I think I dim the light, then you can see when the flame is starting. Yes. So I will do that. And this, I hope it's getting not too dark. So power is on. No smoke, that's good. What's about our heater? Oh, our heater is heating. So the tube close. And if we are lucky, can you see it? I don't know if you can see it. So here. This is the nice blue color. I don't know if I can. Yes, here. It's difficult to show. Maybe I get the right angle here. Now you see the nice purple color of the flame inside. So now we're switching on our frequency, 2 kilohertz. Now the volume pot, we will see. There it is. 2 kilohertz, 3 kilohertz, 4 kilohertz, 5 kilohertz, 6, 7, 8. I think it's a bit difficult with the camera. I don't know if the camera can capture these high frequencies, and also I don't know if YouTube you can hear in YouTube this high frequency. 10 kilohertz, I can hear it. 15, I can barely hear it. So my ears are not so good. I'm too old. And but we can measure it. So we will make also a measuring session where we measure all these devices here, and I can show you how good these things are. Yeah, going back to 2 kilohertz. Yeah. So if the tweeter is running, don't touch any of these parts here. So when the tweeter is running, this is, you see the spark? This is a high frequency spark. So for this, don't touch it. It burns your fingers and is very dangerous. Maybe you are dead after. Okay, so next I will close our little power supply. And no, I will not close the power supply because we want to measure the transformer and the input. So next I prepare our bench for measuring frequency response. I'll be back soon. Now we have here on the bench a little experiment. I have connected the oscilloscope with the probe here directly here to our modulation transformer and the circuitry of the power supply. And what we are hearing now is 2 kilohertz, and on the oscilloscope I make now a full screen sinus. So this is a full screen sinus. If I drop the frequency, so we have 22.55 dB. If I drop it to 19.55 dB, that's minus 3 dB. And this is the measuring border for the frequency. So minus 3 dB is this size. So going back to 22.55, we are at full scale on the oscilloscope. If I now increase the frequency until I reach this point of minus 3 dB, then we have the upper frequency limit of our transformator. So I go to frequency, we have 2 kilohertz. We go to 5 kilohertz, we are on full scale. We go to 10 kilohertz, we are also on full scale. We go to 20 kilohertz, we are also on full scale. I don't hear anything because 20 kilohertz is over the frequency my ears can hear. So we go further, 30 kilohertz. So 30 kilohertz, we have a full scale amplitude. This means this tweeter is now radiating 30 kilohertz. We don't hear it, but the tweeter can do it. So if we go now to 40 kilohertz, there we have the drop minus 3 dB. So the high frequency border of this little transformer in our circuitry is 40 kilohertz. That's the double of that what we can hear. More than double. So I think this little transformer is absolutely enough for the circuitry. So going back, 30, we are full scale. We can look if it's 35 kilohertz. 35 kilohertz, it drops a little. And then 40 kilohertz, we on minus 3 dB. So this is the upper limit of the modulation transformer. This is not the limit of our tweeter. So the tweeter can go higher much more. But I think 40 kilohertz is enough. Now, this is a different circuitry. The last circuitry we measured the modulation transformer in our little power supply. Now I have built a little circuit, this one. This is an RF receiver which is connected through a cable to the oscilloscope. And this receiver receives the RF, which is coming out here of our plasma cell. So this is the RF frequency which make the flame and transports our modulation. So I have no microphone which goes up high, 40 kilohertz, so we can look about the modulation. So I have now 5000 Hertz, and if I put on the modulation, you can see that the RF, this is what you see here. So this is the RF, 27 megahertz. This is our carrier. This is our carrier frequency, 27 megahertz. And if I now put on the modulation, we see that our carrier is modulated, and this is what we hear. This is the modulation we hear. So when I now switch to 10 kilohertz, modulation goes higher. There's a slightly trigger problem in the scope, so okay. Then we have the same height as the 5 kilohertz. So 10 kilohertz is the same height. When I switch to 20 kilohertz, we hear nothing, but the modulation is there with the same height. That means the same sound pressure. If I now switch to 30 kilohertz, the modulation is still there with the same height, it's the same sound pressure. If I switch to 40 kilohertz, then we will see it goes smaller. So this is our modulation transformer. The modulation transformer now transports not so much energy to our oscillator, because the modulation transformer is on his upper end. This is 40 kilohertz. If we switch to 50 kilohertz, we will see modulation. So there's modulation and there's variation 50 kilohertz, but with a smaller amount, slightly smaller, not much. But we can go higher. We can go to say 70 kilohertz. There's almost something there. But as I mentioned before, this is the modulation transformer. This is not our oscillator, and this is not our plasma, which limits here the frequency. This is only the modulation transformer. If we build in a modulation transformer which is capable to transport 100 kilohertz, you will see 100 kilohertz out of this tweeter with the same amount as the other frequencies. I can switch down to 2 kilohertz. Or 5 kilohertz. Or 10 kilohertz. This is a ugly tone. I switch to 20, I don't hear it. This is 20 kilohertz. This is our 20 kilohertz tone. Yeah, this is what's coming out here. This is the modulated RF. You see, when I'm touching this device, it goes away. Yes, so these plasma tweakers are capable to transport frequency in very high ranges. It depends only on what we are putting in. So the carrier frequency 27 megahertz is capable to transport other frequencies, tone frequencies, far beyond 100, 200 or 300 kilohertz. It's only limited by the modulation transformer. But why should we do that? We don't hear it. So the benefit of plasma tweeters is the fast attack. So when this circuitry is able to reproduce 100 kilohertz, then the attack rate is high. And this is what you hear, though there is no distortion. You see, there is no distortion. We can go high in the frequency, we can go low in the frequency, you see no distortion. Of course, there's a little distortion in the circuitry, Yes, it's but it depends on the modulation transformer we build in. Okay guys, that's for now. I hope you enjoyed this little practice and this little tuning and this little measurement. The tweeters are now ready. I will make a setup on my stereo device and we'll listen to them tomorrow. Okay, thank you for watching and bye to the next time.